Hello and welcome to our EC492 presentation on 3D animation creation using IMU data. My name is Ayan Abbas and I worked on this project alongside Ishan, Kashyap, Harjot, Singh and Muhtasim, Haque, Shadab. The client for this project was Karla Beltran from NCBL. Our project tackles the issue of workplace-related musculoskeletal disorders by using inertial measurement units. We have engineered a system capable of rendering real-time 3D animations, closely mirroring the movement made by the subject wearing the sensor, providing a tool for ergonomic risk assessment. The core of the system is an application which uses Movella XSense.IMUs provided by the client. The system captures the data from the sensor and produces 3D animations in real time. Additionally, it translates these movements into graphs, making complex data understandable. It also records the animation and saves the collected data for further research. The achieved outcome of our project is an operational system that not only displays the animation but also consists of an interface to control and record a session, and it is a step forward in ergonomic assessment technology. And now let's dive into a live demo.
So this is the demo of our app. So this is the sensor and this is the strap that we are going to use to strap the sensor to the body. So first I will turn on the sensor. So you see the green light, so the sensor has turned on, and now the amber light is flickering because the sensor is in broadcasting mode, which is that it can be connected to the device via Bluetooth. Now we will place the sensor on subject's body. The precondition is that the subject should be standing in T-pose.
So we will be placing the sensor on the subject's body in this orientation and we will attach it.
So the movement made here by the subject, it will be replicated onto the front end. So the subject is moving its left arm and those animations will be shown live, live streamed on the front end.
So this is how our user interface looks like. So we have 4 tabs: settings, sensor information, start assessment and home. In settings tab, we have given the user the option to set the recordings directory, which will store the recorded session and CSV related to that session. So user can set the recorded directory in this way. You click on this and select whatever directory they want and click on choose. And now we will go to sensor information. So sensor information basically displays the information about the sensor, like which sensor is used to build this system and from where we are getting the data for the live animation. And then we have home tab. So home tab will show all the MP4 videos that are in the specified folder, and if I select a new folder which does not have any MP4s, it will not display anything, no recording found. And then we have start assessment. Start assessment have 4 sections. This is where the animation will come. This will be the roll chart, pitch chart and yawn chart. And we have 2 options, start and stop. If I click on start, it will start the recording, and if I click on pause, it will ask me to save the session or not, and I can save it or I can just discard it.
So this is our session looks like. As you can see that our 3D animation model is present in the box, and now our subject will move his left forearm up. So as you can see that the model also replicates the same movement, and if the subject moves his left forearm down, then the model moves its left forearm down too. So by using these buttons, you can basically start and stop the recording. If you click this, then you begin recording your session, and you can record for as long as you want to. And if you click on the pause button, then you're given the option to save the session and save the recording file. If you click on save, then you are given the roll, pitch and yaw graphs, which tell you the rotational done in the X, Y and Z axis by the subject. And you can view the recording and the CSV files in the folder that you selected in the first step. So this would be your directory. So as we can see that this is a directory we chose in the application, and once we save our recording, our CSV file and our recording file are saved in the same directory, and the recording file is in the format of an MP4. So when we go to the CSV file, we can see all the quaternion data being stored, and also the user data, which is basically the role, pitch, and yawn. So this data can be used for later verifications and later usage, and also can use for research purposes if they want to use it for research. And when we go to a recording, we can see that the animation in the recording is actually pretty smooth. And the reason for choppy animation in our application is that it's coming frame by frame. So due to the latency of merging the frames together and real-time transmission, the animation is choppy in our application, but it's pretty smooth when it is being saved as a recording in an MP4 format.
So now we have ended our session. So when we click on the home page, we can see all the list of recordings made by the user, and this concludes our demo.
For our project, we were able to do real-time motion visualization on the front end of the user's local machine to allow the users to see the 3D human model movements being mimicked as the subject's movement wearing the sensors. We were also able to do graphical representation of joint rotation in the form of roll, yaw, and pitch graphs, and these values are basically rotational values on the X, Y, and Z axis. We were also able to allow the user to start, stop, and record each session, allowing them to have full control of the session and let them decide if they want to start the session and when they want to stop the session, and if they want to record the session for later use. We were also able to save the session data and recordings on the user's local machine, allowing them to see the data collected and the recordings later on, so they could see how the data flowed and how the data changed over time based on the movements of the subject, and also check if the recording was proper and what the subject did later on, if they have to basically see the recordings and make sure that the movements were accurate or inaccurate. And we were finally able to create executable files for the Unity project and the Flutter project, allowing them to run on any Windows PC.
So now coming on to the part, what did not work for this project. Firstly, we encountered latency issues when multiple sensors were connected, which led to inaccurate animation. We identified two potential root causes for this problem. First can be that the sensor did not have efficient synchronization mechanisms, which caused the delay in receiving the data, which in turn disrupted the fluidity of the animation. The second reason can be that the Unity server itself, which creates the animation, was not able to handle multiple data streams coming at once, which could be addressed by creating a multi-threaded server. The other big issue that we faced was when the sensors are connected to the system, it is hard to find the orientation of the sensor. And if the sensor is not placed in correct orientation to the body, then it can cause motion in opposite directions, meaning if I'm moving my arm up, the animation will show that my arm is going down. So for the third one, we inspected the MATLAB code that was provided by the client to get the joint analysis graph for different joint angles. After close inspection, we figured out that MATLAB algorithms were not really compatible for all the angles in the body. It was just specifically designed to work with foot angles. And in order to make it work, we had to do some major revamp of the algorithms to make it compatible with all body joints. And the last issue that we faced was creating a single executable file. The main reason we weren't able to create a single executable file was that the Flutter did not allow to run Python from executable, as it required a native Windows platform channel to make the Python backend run from executable.
Now we want to talk about the future steps that we have planned to improve our project and also create a better ergonomic assessment. Firstly, we want to enhance connectivity to our IMU sensor using multiple Bluetooth dongles to handle multiple sensors. This will reduce latency and improve data accuracy. We can also use Bluetooth with better sensors that have a wider connectivity and a more accurate connectivity as well. Then we can implement multi-threading for smoother animation, where we can use one thread for each sensor. This would increase speed of data collection and also stop data overlapping and help us create a smoother human animation. Next, we can integrate joint analysis using MATLAB. To have a better ergonomic assessment, it is good to have joint information, joint mobility information, which can be used to detect to assess human movements, and we can implement those algorithms using MATLAB. Next, we can upgrade the sensor technology to enhance the accuracy of the data. So we can use better gyroscopes and magnetometer that are used in the IMU sensors to have a stronger calibration and less error in the data. Next, we can develop a custom bodysuit for proper and stable sensor placement. So it is very important to place the sensors on proper orientation and in the fixed position to collect human movement data. So currently we are using body straps, but a bodysuit would help us stabilize this placement and would increase the accuracy by a lot. Next, we can implement machine learning for sensor data interpolation. So whenever there is an error in the data and there is an outlier in the data when using the sensors, those can be minimized or neutralized by implementing machine learning, creating a more accurate motion system. Next, we can include the feature to create 3D models for disabled user. So for if someone doesn't have an arm or a leg, they can also use our system to assess their movements and be a part of this project as well.
To sum it all up, we designed a system which is efficient for assessing human motion, generating real-time 3D animations when operated with either one or two IMUs at one time. We were able to generate graphs of rotational data to further analyze the motion, and we developed a user-friendly interface that enables control and recordings of the session. We successfully met the minimum design requirements set in the beginning of the project and would like to thank our client Karla Beltran and Dr. Steven Knudsen for their guidance and support throughout the project. And thank you for listening to our presentation.